second part of this webinar is will be presented by Dr. Vinod V.T. Patil. So these are the two distinguished speakers with us in this afternoon. So I'm very happy to introduce Professor Miracelo Cernick, who is working in the area of the decontamination, wastewater treatment, and all that. It's a very vast, the experience that he had. So he born in the Czech Republic, received his PhD in natural sciences at the Swiss Federal Institute of Technology, and he's a professor and the director of the Institute of Nanomaterials, Advanced Technologies and Innovations at the Technical University of Liberec at the Czech Republic. When I was looking into his biodata and the publications, what we have observed that he has introduced a lot of the newer technology and the applied type of the work that he has conducted. So we are very fortunate enough today to listen him. So his primary focus is research of the green technologies in the material preparation and application, new in situ remediation technologies for wastewater treatment and other environment-friendly technologies. He is the author of more than 190 scientific papers, which is having more than 5,000 of the citations, having the H-index of the 30 based on the Web of Science. So he will be talking on the very pertinent topic, which is the green technologies for treatment of the contaminated waters. So may I request Professor Cernick to present his talk.
Okay. So thank you, Professor Tiwari, for introducing me, and thank you all of you that I have the opportunity, a chance to speak to you through this webinar and present our institute, our activities, and my activities, which I do in the field of water remediation and similar topics. Well, I had to prepare also one slide about myself, but thank you. You taught everything about me, which was important for the introducing. And so I will start to show you where we are. We are, of course, in Europe. We are in the middle of Europe, in the center of Europe. You can see the Czech Republic, and if you look at the map of the Czech Republic, you see the Prague. Some of you may know Prague because Prague is a very nice capital, historical city. But we are in the Liberec, which is the red triangle north of Prague. This is close to border with Poland and Germany, and the city is in the mountain. In the winter we have a lot of snow, which is on the picture. Of course, nowadays we have also summer here with today nice weather, but in winter we have about 5 months of snowing here. Only to introduce that the climate here is different from the Indian one. So our technical university of Liberec has 7 faculties plus 1 institute for nanomaterials, advanced technologies and innovation, where I am the director of. The university is small. If I look in Indian size, we have only 6,000 students and more than 1,000 staff and about 70 professors. And our institute is pretty new. It was actually established in 2009, but the building, which is on the picture, was open in 2011, and our operation started in 2012. So we will have this year 10 years of celebration of 10 years of operation. And the institute focus mainly on the preparation application of the new materials, mainly nanomaterials and advanced industrial design and technologies. The institute is, I would say, relatively large for our size. We have about 200 people, from which is about 150 are the scientists. We have also here coming people from other faculties to work on our equipments and with our people. And we have also 3 people from India, and one of them will talk after me, Vinod, but we have some other people, and we have people from about 20 different countries around the world working in our institute, and we of course cooperate with many countries. As I said, the institute was established for 2 fields. Nowadays, we have 3 fields of science. The first is material research, the second is competitive engineering, and the last one is system integration, which is also needed nowadays. So the material research is focusing on research, development, processing, but our major task is applications of new progressive materials, and especially nanomaterials in different fields. And during my talk, I will concentrate to application in the field of environmental protection and water treatment and such technologies. The second direction is competitive engineering, where we focusing on development and application of the advanced engineering construction technologies. We are strong in mechatronics system. We are strong in new propulsion units for machinery and for vehicles, and also processing of new materials, including the 3D printing techniques. And the last direction is system integration, where we focus on the software solution and data processing, synergy between devices, communication tools, and also robotics, collaborative robotics, sensitive robotics, and such things which are related to IT. Okay, if you look at the first direction, material research, we have four departments. The first is Department of Environmental Chemistry, which is focusing mainly to application of different chemical processes to treatment of pollution in mainly in water, but also in soil. We apply different oxidation reduction processes, also biological processes, together with Department of Applied Biology, and combination of the techniques to really treat contaminated water, because here in the center of Europe there is many sites on places which are contaminated by former industrial production, which was not environmental friendly, and such sites needs to be treated, because the drinking water is also in the middle of Europe starts to be a serious problem due to the climatic changes. The second is Department of Nanochemistry, which focus on preparation of new nanomaterials by chemical synthesis, organic synthesis. For example, cyclodextrines, which we try to apply in different applications, also in the field of environmental protection. The next department is Department of Applied Biology, which concentrates mainly to 2 topics. One is the application of life sciences, especially applications of the nanofibers. I will talk about it later. And also application of the biological methods for decontamination of contaminated water. And the last is Department of Environmental Technology, which is concentrate mainly to drinking water and wastewater treatment, and some membranes reactions, membranes technologies, and such things. If you look at the other directions which are for our topic nowadays, during my talk are not so important, so only to review, is the Department of Machinery Construction, which is classical machinery construction for local industry, because our city is close to Mladá Boleslav, and Mladá Boleslav is center of the Škoda car industry. You may know Škoda car because it's also produced in India. is part of Volkswagen Group, and we do a lot of things for them. There is also a department of vehicles and engines where we test some engines for them and brake systems and similar things. Then we have the Department of Advanced Technologies, which is mainly the 3D printing and advanced materials, where we concentrate our activities about new surfaces, modification of surfaces to make them harder or make them hydrophilic, hydrophobic, and such things. And the last direction is, it doesn't work now. I don't know why. I cannot. Okay. Department of Software Architecture and Development, and which mainly works about programming. Then we have the Process Modeling Department, where we do some simulations of physical processes. Then we have Physical Measurements, where we are able to measure the physical properties of the materials, and the Department of Robotics and mechanical systems. So that all these departments somehow try to work together for different projects, which I show you later. If we concentrate more about the environmental chemistry, as I said, our activity focus on application of new methods for water purification and treatment, and especially its use of nanomaterials for remediation processes and wastewater treatment. I have some examples later in my talk. And also important question is the potential risks, environmental risks of nanomaterials, because it's still taken as a new materials, and people are scared about potential risk of these materials. We have some laboratories researches. I will not go into details. As I said, our second field are biotechnologies for degradation of the xenobiotics, and also development of the new technologies using, for example, biofilm reactors for different type of contaminates its water, like phenols, cyanides, aniline, chloramines, and these are just examples. We also do some activities about delignification of groundwater and changing of the processes in classical water treatment plant, especially in direction of new contaminants like antibiotics and other substances which are in very low concentration nowadays in wastewater, but they are very dangerous for microorganisms and also for humans. Evaluation of the bigger biodegradation and toxicity. Also, we do some biodegradability tests of materials, and also we have the wetland system for treatment of different type of water. I will show you one example of European project where we use the wetland system for treatment of linden contaminated water. Our next direction is environmental microbiology and molecular genetics, because for the application of these biological methods, it's very nice to see the types of microbes which are there, to identify them, to be able to even manipulate with the genomic information, and try to a little bit change the type of sequencing for application or for modification of such microbes to be more successful in treatment of the contaminants. And we have some methods which are described here. And one important thing which is related to our institute and to our university is the production of nanofibers, because we started at the university about 15 years ago with the industrial production of nanofibers by electro spinning methods, where instead of using the needle technology, which is on the picture up. We used very sophisticated new methods based on the roller or string now, which is on the picture down. And this technology is able to produce nanofibers in very high quantity. And a lot of our activities are related to application of the nanofibers in different fields. Here is some example of making some mesh which is used as a scaffold for production of the biofilm for wastewater treatment plant, which is on the picture most right, where we are able to intensify the process in classical wastewater treatment plant by adding these sheets there where biofilm is grown, and the biological processes of the wastewater treatment plants are intensified. One of the important things which we work on is the remediation of the contaminated groundwater by chemical and biological method, where we used in situ chemical oxidations and in situ chemical reduction. And one of the method which I am personally interested in is application of the zero valent iron particles, nanoparticles, for remediation of chlorinated solvents. And of course, we are university, but we cooperate with a lot of environmental consultancies, not only from the Czech Republic, but also from abroad, about application of this method. Because we are institute and we need money for our research, and we don't get any direct support from the government, we do very intensive cooperation with industrial partner, and we do it through some joint projects, or we do it through some direct contracts. And I have some picture here which are not up to date, but it shows that every year our budget is about 7 million euro from the nature Czech and international grants, international projects, which are mostly with some industrial partners. And we also got about 2 million euro every year from direct money from industry through some contract and the research connected with the contract, so that we really need to work hardly to get the money and to be able to pay people. So it was general about the institute, and now about the topic, which is application of the green technologies for treatment of water. This is a general picture where Vinod Padil will explain you more in his lecture. But the principle is that we take some natural products, for example, some bioextract, three gums, which I show you. And we do some simple chemical reactions, some simple chemical synthesis, green synthesis in microwaves or by heating. And we produce some bioengineered materials, nanoparticles, or some other materials, which is biodegradable. And it's environmental friendly because it's made from the natural products, and it's also biodegradable, so that compared to oily products is of course the friendly. Here are some examples which is based on your Indian trees, on different type of gum trees. This is Kondagogu trees, which we mix with alginate, for example, make a cross-linking and make some aerogel, which is on the picture right, which is very light and is able to absorb different things. And here are small examples how we absorb two chemicals, chloroform and dense liquid diesel and chloroform from water. so that we are able to absorb about 15 times the volume of contaminants compared to the materials which is in the sponge, so that there is about 95% of the space of the pores in the materials. And advantage of these materials is also biodegradable and clean, so that it's very environmental friendly for environment. So I spoke about electro spinning. Here I have some example how the electro spinning works in our institute. On the picture right, you have some production. This is from some tip, and the blue lines are just nanofibers which flow from the one electrode to the other electrode, and so they are formed, and we are able really to make, for example, from the materials which is here, another Indian gum, Karaya gum plus PVA. In the mixture, we are able to make such a film, which is on the right, and such film can be also applied for example, here for material for food packaging. This is rice and corn, so that again, instead of using classical oil products, we use the environment materials which are based on the renewable materials and which are biodegradable. And if you throw it to nature, away to nature, it will disintegrate within a few months, so that or if it goes to the river and to the sea on the way, it's also biodegraded, so that the problem which is now with a lot of waste in sea it can be reduced by application of such technologies. So I would like to show you more picture about remediation of the contaminated soil, application of zero valent iron nanoparticles. The problem is that, of course, industrial production makes a lot of waste, and one of the waste is seepage from the tank, and in many cases we use some chlorinated, or mainly historically used some chlorinated hydrocarbons like tetrachloroethylene, trichloroethylene in the industry, and these were stored in the tanks which were not protected against leakage, and there was leakage from this tank, and it makes some contamination plume, which is in the red color on the picture. And of course, this goes to groundwater and contaminate groundwater, which is not drinkable. It also can come to surface water and contaminate other waters, so that such site should be somehow remediated. And remediation means that you do some processes, you apply some techniques, how you decrease the contaminants. One of the possibilities, dig everything out and store it to some landfill or some waste disposal site. Of course, it's very costly and it's doesn't work. So instead of using the physical methods which are mentioned here, like excavation, we can use also some other methods like pump and treat, soil vapor extraction, air sparging. These are the physical methods, but we mostly test in our institute chemical and biological method. And chemical method, we have the chemical oxidation, which means that we oxidize the contaminants to something which is not so dangerous, not so hazardous, or we do the chemical reduction. And we can combine these methods with microbiological activity like microbial bioreduction together with chemical reduction to treat these waters. The principle which I want to show here is that to contaminated groundwater, which is in the red, shows that this is some contamination. We make a drilling, we make a borehole, and we inject something to the groundwater, which react with the contaminants there and reduce the contaminants to something which is not so dangerous. And one of the examples is application of the nanoparticles of iron. The principle is used for many years in so-called permeable reactive barrier, which is on the picture down, where you construct some barrier which you fill with the iron shavings or some flakes, something from industry, and this iron is reactive and it's able to react with contaminants. Such reaction is simple, but it has some limitation. Of course, you need some space to construct these walls. You need some. You have limited by depth of the contamination. In many sites, you cannot make such drillings. It's also costly. And with some type of contaminants, this microscopic iron doesn't work. The principle of the application iron is shown in this picture, where we have trichloroethylene reacting with zero-valent iron. This is oxidation reduction process where iron is the electron donor. I hope I don't go too much to chemistry. And there are some chemical acceptors, it can be chromium, or in this case, TCE. And it sort of changed from chlorinated hydrocarbon to non-chlorinated hydrocarbon, which is, of course, not so dangerous and toxic. And in our case, we used nanoparticles, which are on the picture. These are particles about 80 nanometers in diameter. And the advantage of these particles is that they have very huge surface area and high reactivity, which is on the picture on the right side. Where you open them to the air, they burn because they are really very reactive. And on the picture left, you see how the reduction process works with, for example, lead, or with this chlorinated hydrocarbons on the surface of these particles. They are reduced and they lost the chlorine, and you change the trichloroethylene to ethylene, which is gas and which is not danger compared to the original particles. Here is some reaction result from laboratory, which shows that within 1 hour you are able to treat in some condition this trichloroethylene. But this is not the biggest advantage of nanoparticles. They have another advantage, and this is that they are so small that they can migrate in the soil. Compared to the microscopic iron, which of course it's not able to migrate. The particles in these sites are able to migrate with groundwater and go from one side to the other, to migrate to the distance of few meters, which is shown in this laboratory column, where from the bottom we inject the nanoparticles, and you see how they move through the column, and the color is changed because iron is black. So that you see how the particles are moved. This is how it looks in reality, in full scale, because we apply this method in many sites, not only in Czech Republic, but also in other sites in Europe, where you have some, if you go from the right side, you see the tank with the reactive particles. You mix them on the side to make some suspension. There you add also some surfactant to be more reactive, or less reactive, but more transportable. And then you make the final concentration, which is about 1 gram per liter, relatively low, and you pump such suspension in a few injection wells, which are on the picture here. These wells are about 25 meters deep, and you are able to inject them there and apply them for treatment of contaminated groundwater. I don't know if this will work. I will try. This is picture, one more picture from laboratory, where we have the about 2 to 1 meter big aquarium, where from the back we inject the nanoparticles, and you see how the nanoparticles are moving in the soil, so they are really able to move. And this is the page, as I said, basic advantage of these particles compared to microscopic particles, that they are able to move and to react with contaminants which are distant from the injection well. Okay, it's at the end. And here is one example of the real application in the field, where we have the contaminated site. Initial contamination is on the picture left top, and the concentration of the PCE tetrachloroethylenes are up to 50 milligrams per liter. And then the picture is about up to 3, 6, and 9 months of treatment with the zero and iron particles. But this is not permanent treatment. This is that we inject them at the beginning, and we let them react in the soil and in the water. And you see that if you compare the picture original of contamination plumes and the final, you see very big difference, so that the site is almost clean and the majority of the contamination disappeared by the reaction with this zero valent iron. Also, the advantage of this method is that these nanoparticles are oxidized to iron oxides, which are normal minerals which are in the soil, so that you don't produce anything which is not natural. And this is again the green technology, because you add not some danger chemicals like chemical oxidation process, for example, but you add the chemicals which is nature for the soil. So, and last few slides I have about another application which is which we work on within the European project, project LifeWatt in the call Life, and the project where I am the principal investigator is about treatment of the linden hexachlorocyclohexane, which is one of the pesticides which was used in 60s and 70s all around the world, in India as well. And there is many sites around the world which are still polluted by this persistent chlorinated compound, which means that nature has not tools how to treat these chemicals. And our aim in this project is to construct 2 wetland systems for purification of this linden contaminated water and transform them to non-contaminated waters. And one of the sites is here in the Czech Republic, another is Poland, and of course we do some other activities and dissemination. These are the sites on the map of Europe. The site which is called Hájek in the Czech Republic, the contaminants originate from the chemical factories Polana, and the product were transported in 1960s and 70s to this Hájek dump site, which I show on the picture here. And it was just stored them randomly distributed in this relatively big area. But nowadays the drainage water from the site contains a lot of this persistent organic pesticides, HCH, the total amount which is on the high side is about 5,000 tons. Of course, this drainage water goes to river system, and it's able to contaminate the river system around. So our idea is in the bottom of this pile to make such a system which is based on few steps. The first is aeration and sedimentation tools. Then we have the reactive barrier with iron chips. Then we have an anaerobic biosorption unit, and the last step is the aerobic wetland for final treatment of water. And this is how the site looks in the full size here, where we have the injection of water from right side through the sedimentation tanks, the reactive barrier pools, then biosorption system, and the final aerobic wetland. The system started operation in September last year, so that we are still in the testing mode, but we are able to reduce the initial concentration by 95% now, so that the final concentration is about 5% of the original concentration of these linden-like compounds. So and at the end, I have just here a picture that, excuse me, where is the nanotechnology department? And the scientists say you just drop on it, but you saw that on in my presentation that we have much bigger departments on nanotechnology than on the nanoscale, which is on this picture. So thank you for your attention, and I am sort of ready if you have some questions or something, some comments to my talk. Thank you.
Thank you, Professor Cernick, for your wonderful talk. Very good glimpse and the overview of the activities that is going on at that the institute or the university. So we are very happy to see the wonderful presentation. So there are the few queries, I will say that. So if anyone is having the query, they can put it on the Q&A box. Meanwhile, I'll be taking, sir, a couple of the queries that we have received. So one of the queries by Professor Prasad, he is asking that, is it possible to remediate inorganic and organic contaminants in permeable reactive barriers? Please give one example, if possible.
Yes, we are able to, actually, we work only with the reactive barriers filled by iron, and we are able to treat the chlorinated chemical organic compounds. This is our major task. We also tested for fluorinated compounds, which are nowadays also the one of the modern contaminants. But we are limited to this chlorinated and fluorinated, also brominated compounds. Yeah.
Okay. I think this must be clear. So the question is that, is it possible to apply natural contaminants like fluorine and arsenic removal in groundwater through nanotechnology?
Yes. We arsenic and chromium are not so difficult to make the chemical reduction, so that it works very well with the chemical reduction methods like zero-valent iron, but it can be some sulfur compounds which are less expensive compared to the zero-valent particles. And this is simple process that chromium-6 you reduce to chromium-3, which is precipitated and of course not so toxic, because it's not, the concentration in water is significantly reduced. So that in general chemical reduction methods are good for arsenic and also mainly for chromium contamination, which I know it's on many places in India. Yeah.
A similar question is being asked that the zero-valent iron, can we treat, can we use it for the heavy metal toxicity in contaminated water?
Yes. Yes, we also tried, for example, for uranium, and because close to Liberec there is a site where uranium was exploited by in situ chemical leaching method, which means that you inject sulfuric and nitric acid to the soil and dissolve everything there and pump it out, and you extract uranium. But it means that you have site where the pH is very low, and there is a lot of different heavy metals in this water. We also try to make a reaction of zero-valent iron nanoparticles with such water, and and for most of the contaminants which were there, we are able to precipitate them and to reduce the concentration of most of the heavy metals there to much lower concentration. But we have done it only in the laboratory columns and in the batch reactions, not in the field.
Yes. So these are from the audience, these are the few questions or the queries. I have some queries. Actually, we are also working on such kind of the advanced materials or even the coated materials, or I can say that the kind of the engineered materials also we tried and we have synthesized and all. So the very first thing that I wanted to know that the zero-valent iron, which you have, we are using it, how you are synthesizing it in the laboratory, and what is the the applicability or the cost effectiveness and all that in the first thing. And second thing, when you are injecting, say for example, the groundwater, the treatment and all, the decontamination or remediation of the groundwater, so naturally this iron will remain there if it is getting reduced, say Fe2 plus, as you mentioned that, and then it will be iron oxide, in fact, based on the pH and all that. And that will remain there, and it will be, if it is absorbing the contaminants. So contaminants, of course, will be concentrated at a particular point, and then it may again leach out to the environment. Just we wanted to.
Yeah, I understand. The first question is that we prepare. You can prepare, of course, the nanoparticles in laboratory by reduction of the boride, but by boride. But this is
chemical reduction.
Yeah, but this is not green technology. But
yes, right.
There is a company here in Czech Republic which is called Nano Iron, and they produce the nanoparticles by reduction in oven by hydrogen. So this is an industrial production. They are able to make kilograms or tens of kilograms of the nanoparticles, which is enough for such applications. So that there is a source of nanoparticles. Of course, they are not cheap, but compared to the other method, they are sort of applicable because you need a small amount. The second question is about the iron oxide nanoparticles. Of course, they have a relatively big surface area, and they are able to absorb the potential contaminants. But if the contaminants are sort of absorbed on these particles, they will not release in a moment. And there's also very often some biological processes. In our technology, we combine the application of the nanoparticles either with biological methods. We add some, for example, some source of carbon for microbes that they help also to reduce the contaminants, so that this is combination of the chemical and microbiological process. Or another method, we use the DC current. We use the electrodes, and we apply the electrokinetic method for treatment together with these nanoparticles, so that we are able to really to reduce the concentration, and the nanoparticles itself, after the oxidation, they will of course consist some contaminants, but they will be either very slowly released or mostly treated by microbes, which are also in the soil, so that the final so to say, the state will be that iron oxide will be finally clean of contaminants as well after some time.
So, but in either case, the iron, the soil will become iron rich.
Yeah, but as I said, we applied about 1 gram per liter, so
Right.
that the final,
of course it is.
There is a lot of natural iron oxides in the soil, so that
it's added advantage, because the nanoparticles we are using, so very less amount is required. So of course, because zero valent iron that we are trying. So it's a great the presentation, sir. So we all the applied part, we try to do certain things in the laboratory, but how to, in a greater extent, how to use it or to apply the technology, that is the big challenge usually people they used to face. Anyway, that it was a very nice presentation. So I do not know, VC sir is still.
Thank you very much, Cernick. It is a wonderful presentation. In the initial stage, 5 minutes, I was disconnected because of my internet problem. But I will be watching again the recording. I will take again and I will watch again for that. And thank you very much. I was there. Wonderful presentation, and a lot of appreciation from the participants also in chat box. They're all appreciating your presentation. It's a wonderful. Thank you very much, and we'll be in touch.
And I thank you for invitation, and we are sort of open for any cooperation, so that if somebody wants to cooperate with us in the field of this technology, we are very open, and we of course will share the knowledge, and okay.
Thank you very much.
Thank you for the invitation.
Thank you, sir.
Thank you.
So please stop sharing slides.
I do.
Yeah. Okay, thank you, sir. So, sir, shall we go for the second presentation?
Yes. Yeah.
The second speaker, the resource person, is well known to us, of course, Dr. Vinod V.T. Patil. He used to publish in a very high impact journals that we have seen. So he will be talking about the bio-based functional materials and their advances in environmental, food and energy applications. So before I request him for his presentation, I would like to introduce him. Dr. Patil is an assistant professor and senior research officer at the Institute for Nanomaterials, Advanced Technologies and Innovation, Technical University of Liberec, that's the Czech Republic. He received his PhD in biotechnology, environmental chemistry from Acharya Nagarjuna University, India. Worked as a scientific officer at the Board of Radiation and Isotope Technology, BRIT, Department of Atomic Energy, India. And he had a vast experience visiting the different institutions, working in different institutions, and variety of the the work that he has carried out. So he worked at the NUS, the National University of Singapore, as a postdoctoral fellow in the Environmental Research Institute, Singapore, and visiting research fellow at Wrexham Glenard University at the UK, and macromolecular chemistry, Beirut University, Germany. He has authored and co-authored more than 100 research papers on his own credit, and 10 book chapters and many research proceedings in international conferences, and having the H-index of 27. His research interests include that the green technology or the green synthesis of the nanoparticles or the nanomaterials, engineered materials, advanced materials, and that is being the the applied part of the materials that he had carried out is the bioremediation using the nanostructures of the 2D, 3D type of the polymer nanocomposites, electro spinning, and bio-based the functional materials for the environment or the food and energy applications. So that he has a vast experience. We are very eager to listen him. So, sir, now the platform is yours. So please go ahead.
Thank you so much, Professor Tiwari, for a kind introduction to me. So I will share my presentation. Yeah. It's okay, sir. It's in full screen. Hello.
Yes, it is in the full screen.
Okay, thank you so much. Yeah. Respected Vice Chancellor, Professor Rao, and other distinguished professors in Mizoram University. Today, I would like to talk about bio-based functional materials and their advances in environmental, food, and energy applications. So, as you know, in this century, this bio-based material contribute into sustainable product development. These materials emerge in the last years an attractive alternative for sustainable product elaboration. In my current talk, these materials preparation, characterization, and potential application in environmental remediation, catalytic degradation of pollutants, food applications, and energy related, both storage and harvesting areas are presenting. Yeah. So this is the organization where I am working. So I am not going for detail about this institution because Professor Cernick has elaborated about the university and various departments and overall research work going on in this university. So in the Czech Republic, there are many universities, around 66 public universities, and Charles University, Masaryk University, Brno Institute of Technology, and Technical University Liberals are among them, and other 54 institutes are under Czech Academy of Sciences. And one of the important things are the Czech Republic total population, only 10 million inhabitants, and the capital city is the Prague. We know some of the facts and figures are this is the 8th safest country in the world according to Global Peace Index 2020.
ये वीसा वाल को भेज रहे हैं ना, ये ऐसे उल्टा करेगा तो कैसा होता है? हाँ, वो उल्टा कर दिया थोड़ा. एक अच्छा करो, ये सेकंड पेज, थर्ड पेज.
Sir, shall you?
Sir, please mute.
Yeah,
sir.
Professor, maybe.
VC, sir.
Sorry.
Yeah, maybe. Shall I continue, sir?
Yes, sorry. Please continue.
Yeah, thank you. These are the different departments in our universities. One is the one among them are nanomaterials in natural sciences and environmental technology, Department of Applied Biology, and Department of Nanochemistry. So all these different departments and the research activities, teaching activity has been elaborated by Professor Cernick. So I am not going in detail these sections. Yeah. We'll talk about the bio-based materials. Mostly my work and my department people work on this bio-based materials and the processing and applications. So as you know, there are different types of bio-based materials and different sources coming from botanical, seaweeds, animal, bacterial, and tree gum exudates. So among the botanical sources, cellulose, starch, and pectin, gorgum are important materials. Among the seaweeds, alginate, carrageen, and agar. For animal sources, we extract chitin and chitosan type of material. Even in bacteria, xanthan gum, gelatin gum, pullan, dextran type of materials. So most of my work concentrate on trees. We are concentrating on the gums extracting from the tree based on Carrea, Arabic, Tragant, and Kondagogu gums. What are the importance of these bio-based materials? They are biocompatible and biodegradable and non-toxic material, and they are economically feasible. The structures are very complex structures. If you analyze the structure of these gums, especially the tree gums, so you can have the main and the side chains. So these are the composition of sugars based structures, and they are hydrocolloids based properties and high viscosities. And these tree gums have different functional groups such as carboxyl, hydroxyl, amino, carbonyl. So these are very easy to conjugate with other molecules to become various. If you can do chemically modified into other materials. So their applications in food, pharmaceutical, environmental, energy, and other biomedical areas very well documented. So today I talk about the mainly on bio-based tree gums extract from different trees and their application in making carbon and microstructures and how they are processing into film, sponges, and fibers. And third section is only the noble metal nanoparticle, how we can synthesize nanoparticle by using these gums and their applications in as energy harvesters and supercapacitor electrodes. These two sections for energy developments and other section for food, mainly for food packaging systems and how these materials, even films, sponges, and composites can be used for pollutant degradation, environmental remediation of water and other toxic metals from the environment, especially for water treatment. Yeah, a brief introduction about the tree gums. We mainly concentrate working on gum arabic and tragagan and guar, gatti, and Carrea and Kondagogu gums. So this I have shown here the fully grown tree gum tree. So when you make a bark on the tree, the gums will come out from the tree and it will get hardened under the sunlight. So lately you can easily get removed. So these are the gum shown here. This gum arabic and Carrea and Kondagogu. So gums are considered as non-food additives. So they are they are non-toxic material and biodegradable in nature and biocompatible materials. Yeah, here I have shown you how the gums can be produced here. So there are different techniques to different methods to make the gums, or by the formation of gums mainly because of this microbial attack on the tree, or if you make a mechanical injury to the tree, it will produce the gums, and chemical injury and even water stress or insect attack. So this process is called gummosis. So the tree will be producing the gums so that we can easily collect it from them. So what are the advantages and availability of these gums. So this mainly advantage for they are natural material and biodegradable material, non-toxic. This material can replace oil-based plastics material for many applications, especially in food packaging, even food carrier bags, or in it can be used for biomedical applications. And these are a new material, and we can do materials with enhanced specific property can be developed through chemical modifications. And other things are this, these gums have empower to rural economy of the country. So you can see here in the world, where the red indicates the countries or the countries where the gums are countries or continent, the gums can be easily available. So especially for India and Africa and North American countries, there are plenty of gums available. So they are very economically feasible material, very cheap material. Get it by procurement, or we can use them economically. It is not at all not much expensive at all. So what are the pros and cons? Actually, why tree gums we use for most of the works? They are 100% bio-based materials. So they are renewable and abundant, present in the nature. And as I told you, it's a low cost, and they are biodegradable. And what are the disadvantage of these gums used in many applications? One is they are high moisture sensitivity. They can absorb water and make a hydrogel form. So they are hydrophilic materials. And for the other packaging application, if you want to make films, they are very poor film formability. So we need some other biodegradable material or other surfactants to improve the film formability of these gums. So another important thing is they have weak mechanical properties and thermal properties too. And for especially for food packaging, we need high barrier materials. So these gums as such shows much less barrier properties. So how we can improve all these properties? So how can make a hydrophobic material out of hydrophilic gums, or how we improve the film formula depends. So we can produce better material from these gums. So these are the structures of the major tree gums used in our studies, especially for a Korea gum. You have different sugar compositions, ramenose, galactose, and glucopyranose galactronic acids. Like Kondagogu also, you can see these are different sugar compositions in different proportions, and to build these gum structures. These are the partial structures shown in the right-hand side. So this just see actually how gums, what are the different types of gums we can be produced by the trees. So these gums are categorized into three important sections, as called grade 1 material, grade 2, and grade 3. So among the grade 1, most of these gums are used for food and pharmaceutical application. Grade 2 and grade 3 are mostly considered as thrown away material, because they have more high, they contain high acidicity in their structure, so that cannot be used for food applications. So these grade 2 and grade 3 material are considered as bio-waste material. So this can be our main research focus on grade 2 and grade 3 material as a bio-waste to valuable material production. So we have used this material for green synthesis of nanoparticles and production of electro spun fibers, and use this material for environmental remediation, and this material used for biocatalysis and biosensor applications. Even this material shows antibacterial property, and later on the food packaging and energy harvesting. So as I mentioned you, these gums can be used for different applications like stabilization of nanoparticle, synthesis of nanoparticles. So about these gums and their applications, we have published in our the journal Biotechnology Advances. Yeah, and the major objectives today, I want to talk about how these gums can be used for green synthesis and stabilization of nanoparticle, and application of these gums in environmental and energy application. And we formed a tree gum based sustainable products, example for films, fibers, and sponges out of these gums and their potential applications, and how we can make these tree gums into electro spun fibers. So, sorry. So among the nanoparticle productions, around 40% contributions are from plant-derived material. So plants are the major contribution of synthesis of nanoparticle. So we could synthesize various shapes and size of the nanoparticle, as is shown here. Can be spherical to branched structures from tree gums. So this synthesis of nanoparticle by using the biogenic synthesis, the green synthesis, this mechanisms, we know these gums can be used as a reducing agent as well as stabilizing agent. So these are the main scheme of the green synthesis mechanism, and the simple method we could synthesize the various different types of nanoparticle, metal oxide nanoparticle can be easily formed. So the in the gum here you can see once if you want to make a different nanoparticle like silver, gold, and platinum, you can take the gum solutions in water and use the precursor, corresponding precursor for the synthesis of nanoparticle. For silver, you use silver nitrate, and gold nanoparticle, HAUCl4. So platinum tetrachloride used for synthesis of platinum. And once you use the precursor and the gum solution in the required amount, just heat the solution at certain temperature, it can be formed different types of nanoparticles. So how these are the characterization steps for nanoparticle when you use the UV visible spectroscopy. So you can find out the corresponding lambda max for the each nanoparticle formation, and the color of the solution also get changed. So it can be analyzed by XRD and FTIR to find out which functional group is responsible for the production of nanoparticle. And if you want to know the size of the nanoparticle, you have got the TM analysis. So these are the main mechanism of nanoparticle mechanism and stabilization of nanoparticle using by tree gums. We use different tree gums for stabilization of zero-valent iron nanoparticle. So in this picture, you can see that the core of the zero-valent iron nanoparticle, and it will be surrounding by the gum structures. So it gives a protective cover to the nanoparticle, so that the nanoparticle stabilization can be extended to extended even 6 months to 1 year. So this material you can keep in the room outside room temperature, it never degrades. So because of the good stabilizing agent, stabilizing behavior of these gums on the nanoparticles. And next, I would like to talk about how these gums can be converted into bioplastic films. So we have made different types of films for food applications. How the process takes place. In the next slide, I will show you how the bioplastic films based on gums can be prepared. So as such, gums cannot be used for films because they have a very poor film formation ability. So as such, gums, you can see they cannot make good films because of the structural and hydrophilicity. So here we use various different techniques to make the films. So we use chemical modifications as well as other material like graphene oxide conjugation with the gums to make a good mechanically good barrier property of these films. So let us see. The main objective is to develop a mechanically stable and freestanding film utilizing these tree gums are very important. So we have reduced the hygroscopic nature of the tree gum by interaction with the other materials like other biodegradable or nanoparticle material with the tree gums. And the resultant material also shows high barrier and mechanical property. And after the incorporation of nanoparticle or other additive like a graphene oxide, this composite films also shows biodegradation. Yeah, this is a formation of tree gum with graphene oxide. So we use different concentration of the solvent and water. So you can see different sonication times and the procedures schemes are described here. And so we made the solution of graphene oxide with the various gums, gum arabic, kondagogu gum, and then we made the films. The films are shown here. So, and this film shows very good mechanical property, thermal property, as well as barrier properties. So here I described about the mechanical property of these films. So when you use the Young modulus and tensile strength elongation rate, so these up to different concentration of graphene oxide, the composite film showed good mechanical properties like other barrier properties like oxygen transference, and also showed very these films are even can be used for food packaging applications. And these are the chemical modification by dodecyl succining anhydride. So if you use the gums and when you react with the DDSA, it can conjugate into DDSA modified gums. So this conjugation can be easily analyzed by FTIR and NMR techniques. So these films showed exceptionally very good barrier properties, mechanical, and even this film shows transparency too. Further important features of this gum is that the whole material, the film showed antibacterial properties. So these materials are good for food packaging applications. And the improvement of hydrophobicity of this material also shows better yield compared to the normal films. And these are the results I have shown you the even thermal stability and as I mentioned you the mechanical property of this DDSA modified gums. And next important section is the synthesis of high barrier and biodegradable films based on Plaque water chemically modified gum condagogo. You can see here we use the sodium hectorate into the addition to the gum, so it can form very nice nitrite structures and improved hydrophobicity of the film and mechanical and other barrier properties. This has been reported to recently. We published this work into the macromolecular material engineering. So after addition of this sodium hectorate, this film showed exceptionally very good properties like barrier and mechanical properties. So this method also environment friendly material. After making the clay modified films, it can easily biodegradable also like a natural gum material. So biodegradation we observed is more than 90%. So here you can see different composition of these materials and how these barrier properties in 50% relative humidity and 75 relative humidity shows this 75% relative humidity condition. This film show good properties, and we compared other available bioplastic in the market. So our clay-based gum composite film shows better position among the other material. And other important research we developed was making the edible films out of these gums. We used Carrier gum and periodic treatment, and we made a Carrier dialdehyde material, and this Carrier dialdehyde we have reacted with the gelatin to form gelatin-based tree gum composites. So this gives a very this material used in edible film, used as an edible films. This material shows good barrier property as well as mechanical property. So you can see here actually the transparency of these films in various amount of gelatin present added in the film. So overall this material shows good transparency, and the mechanical and barrier property also shown in this here. So you can this work has been published in Advanced Sustainable Systems. Yeah, actually this is the overall work we carried out based on the gum-based films. So we have made a tree gum with graphene oxide nanocomposite film, composite films, and this film showed good barrier property, mechanical, and hydrophobicity. And other chemically modified gums like adenine succinyl anhydride modified tree gums also used for food packaging things. So next step is mix the gelatin-based films. The gelatin-based film showed exceptionally good for it can be used as an packaging edible as well as a packaging film. So even the food packaging material in the edible format. So this is another chemically modified gum kondagogu based on Plaque water. So these are the different chemical modification we did for the natural gums to make exceptionally better food packaging materials. And this other bio-based composite material or films we have synthesized by using two different polymers. One is from gum It is Coccolosoma gosway, gum Condagovu, and other is brown marine algae alginate. So these two polymers mixed in various compositions and prepared the films by casting method. This film we have used for food packaging applications, and we have analyzed these gums for the different properties, even water contact angle, hydrophobicity, how hydrophilicity can be improved to hydrophobicity by the combination of these two polymers, and the mechanical strength and biodegradability also. And this film showed exceptionally good properties. Yeah. So here you can see the different films made out of these gums. This is a composite of two gums combined together. So these are very flexible films. So can be used for food packaging applications. So what actually in the laboratory we tested these films for packaging of food grains, and we stored for 6 to 1 year, and the food is shown no other degradation, or then this package material shows non-toxics after biological testing, and even after this package we have shown it was 100% biodegradable too. So the next section I would like to go for the fibers. As Professor Cernick described about the electro spinning, we have made the electro spun fibers of tree gums with additives such as other other polymers, synthetic polymers, like a small amount of synthetic polymers like a polyvinyl alcohol. So it can be easily electrospun, and we standardize our method here to make the electrospun fibers. And these electrospun fibers can be synthesized in huge amount, so industrial scale. So this can be converted into a food packaging material as well as food carrying bags. So these are the process. So when you use the gum arabic, you make the solution with the gum arabic and feed into the electro spinning system. We have the industrial scale synthesis of fabrication of nanofibers by using Elmarco electro spinning machine. These are the electro spinning conditions given here. When you make the fibers, we test the fibers mechanical strengths and other properties. So then we could make the gum arabic bioplastic carrier bag. The process can be like this, and the improvement of fibers, we use plasma treatment and even gamma irradiation make it to improve the property of these fibers, like hydrophobicity and mechanical and other barrier properties. So this is a small video. You can see here how we synthesize the electrospun fibers. So this I have shown you the powder of gum arabic, and when you mix with water, we can have the gum arabic solution in water, then feed into the electro spinning machine. Sorry, something. Yeah. Yeah, sorry for the disturb. Yeah, sorry. This is a video I would like to show you how the biomembrane can be prepared. This is I have show the gum arabic powder form. Then we could make the liquid form of gum arabic, then feed into the electro spinning machine. So when you get the when you start the electro spinning machine, it can make a long fibers. The fibers can be tested for its water solubility in normal water and other water solubility in water. So different forms of fibers can be synthesized, improved by chemical, by treatment with gamma radiation or plasma treatment. So once you make the plasma treatment, these fibers are hydrophobic in nature. They did not dissolve in the water. So this normal, we use the plastic paper for packaging the food. So when you use these fibers are very easy to use for packing the food, just covering the food. Even normal way for the parcel services, or we can make the bag out of these fibers and carry the food. So advantage of this system is this packaging system are completely biodegradable in nature and recyclable too. So according to the natural polymers, during the electro spinning, we made fibers exceptionally good property fibers for application of water treatment, renewable energy, and food industry, and biomedical applications and biotechnology. And this work has been published in ACS Sustainable Chemistry Engineering. As I told you, the different forms of electrospun fibers, how these electrospun bioplastic fibers used for food wrapping or food packaging applications. And we have made a hydrophilic film as you say writing board. You can just see how it's work. So please see this video. So this is a film made out of gum composites, and we can use as a writing pad. So you can write whatever you want, just like it's like a white board. So with marker pen, and you can erase this out. So you can use this film for many times, and erase it. And it's like a biodegradable material, non-toxic writing board. And here you can see we can make this I have shown is a hydrophobic film. The film can be converted to water insoluble film by chemical modifications. So both way we use these films as water soluble film as well as water insoluble film to improve. Depends upon our applications in various fields. Yeah. This is a small video how we recycling this gum packaging films. So you see they are very flexible films and transparent too. When you use the film, these films can be used for packing some pharmaceutical material or any other material for keeping as a stock. So maybe this how this can be recycled. So after the use, the packaging material, you can take it out and put it in water. So this I have to mention here, this is a hydrophilic film. So this can be easily soluble in water. So we can use this film for some materials, material like pharmaceuticals or other normal rice or other food grains for packaging, and these material can be recycled, again putting into water, again casting the solution to make the same film format. So we are not going to waste this material. Again, it can be recycled for many times. So here the other section, I would like to show you how the sponges are prepared out of these gums. We have made different sponges, different shapes, even including we can add some nanoparticle conjugation with this sponge to make various applications. Here, recently we have prepared a bio-based sponge. In this preparation, we used two important gums. Gum is Condagogue and sodium alginate, and mixed together in various ratio and freeze-dried to get a sponge. So both these gums are soluble in water. We got the sponge is soluble in water, means it's hydrophilic in nature. So when you do the silylation, chemical vapor deposition, we could make this sponge as water insoluble sponge. So you can see here the hydrophobic sponge looks like this. Water spots are on the sponge. So they are very lightweight material. This density of this sponge is 18.4 milligram per centimeter cube, and they have shown high porosity, approximately 94% porosity. Porosity is observed in this sponge, and these sponges sponge can be used for, and we have used this sponge for oil organic compound absorption process. So here you can see the porosity of the sponge. This is a micro CT analysis to determine the porosity and pore size of the ensured sponge. So this we have here shown here how the hydrophobicity increases by using the silylation method. So we could observe more than 130-degree water contact after silylation. The silylation material is very useful for the oil water separation. So I can show you how this sponge can be used for diesel water separation as well as crude oil separation. You can see this video. Take the sponge, and this is a mixture of diesel and water mixture. And if you have the mixture of diesel water, just dip it on the liquid, so the diesel get absorbed onto the sponge. And here you can see how the crude oil is getting separated from the water. So these sponges, the advantages of sponges is can be easy method to make these sponges, and they are they can be made into hydrophobic form by simple silylation method, and later they are shown very good biodegradability also. So in normal laboratory, if you have a spillage of chloroform, mainly when you do the work in organic laboratory, or other area of using organic liquids, organic solvents. So here, so it can be if you get some spillage in the ground or some places, so it can be removed by using this sponge. Here I could show how this chloroform can be removed from water. So here we are use some dye to make it color of this chloroform. So this is a chloroform in water. So how this chloroform is getting removed by this sponge? Just in the fraction of seconds, it get absorbed onto the sponge. How it happens actually? So what is the mechanism behind this adsorption? This is a simple capillary diffusion through the spores. As I shown my earlier slide, they have high porous material. There are a lot of porosity of this sponge, so it can quickly absorb this organic solvent by the action of capillary action. So, and later this material can be taken out by simple squeezing. Just you press the sponge, whatever the adsorbed material will come out from the sponge. So it can be recycled for many times. So this work has been published in Advanced Functional Materials, and we tried many of the toxic organic solvents used for absorption studies. Chloroform, ethanol, diesel, even toluene, and other oils like waste oil and even coconut oil, organic solvent hexanes. All this shows a very good adsorption capacity. Yeah. So another important research on we use the two biopolymer together, this chitosan and gums combination to use for making the sponge, and this sponge shows high porosity, and this material easily used for dye adsorption from water. So we have shown the adsorption of methylene blue and methane orange from water. So this shown very excellent results. And the last section I would like to show about how the gum waste into high performance battery material for energy as an energy harvesters. So we have shown here our gum waste. So as I mentioned you, grade 3 material we are used in this work. They are considered as bio waste. They have no use for this use this grade 3 gums. They are just thrown away material because they have high acidic content in the structure, in the composition, so it cannot be used for food application. So they considered as bio waste. So when you collect this bio waste of the grade 3, then started using the pyrolysis at 800 degrees Celsius for 1 hour at nitrogen atmosphere, we can make a carbonized gum. These carbonized gums, again some treatment with the potassium hydroxide and sonication under sulfuric acid, it can make a this carbon fibers. So this again we converted into electrode material and used for high rate of lithium storage. So this work has been published in the Electrochemical Actor recently. So how we can transforming the gum waste into high tap density micron size carbon with the high stable, high ultra stable, high rate lithium storage. So this this work has in this work actually we are again trying for different gums for making the high porous carbon for potential applications, like even this carbon can be used for environmental remediation too. And this is another research used for making titanium dioxide with the gum arabic carbon paste electrode for detection of lead ions in plastic toy. So we have collected many plastic toys from the market and analyzed that they have high content of lead ions into it. So how we can detect the lead ions in the plastic toys? So these are very important research because the toys mainly used for kids. So if they bite it some lead, there is a chance for the lead to go into the digestion system. So maybe it is very toxic to the babies or babies. So maybe your kids, those using the toys. So maybe so how we can detect this highly toxic material present in the toys? We analyze very simple way of making the titanium dioxide nanoparticle, incorporate it to gum arabic and make a electrode material for electrochemical detection of lead ions in this plastic tape. It has been published in ACS Omega recently, this work. Yeah. So this is another research we have conducted on gum waste into energy harvester. So how we have collected the gum waste and converted to nanoporous carbon material. This carbon material can be used for energy harvesters. So this work has been published recently in the green chemistry. So how we can make very easily the energy from the waste to energy, waste converted into energy. So I will be explaining the next slides. So there are a lot of work going on recently on how this water harvester can be prepared and how this can be converted. Evaporation driven water harvester can be prepared and how we can use for energy applications. So this is a scheme of the work we carried out. We used the gum material from the tree and we made the powdered carbon by at 800 degrees Celsius at nitrogen atmosphere, and then activation with the potassium hydroxide and sonication with sulfuric acid. Suddenly we made this nanoporous carbon. These are the scheme of the procedures, what the carbonization temperature, heating rate, and related things, and sonication time. And we made a different gum composite with carbon material from Arabic, Guar, Korea, and Sandan gum, and our yield is good yield from starting to make the end products. So then we have analyzed this carbon nanostructures by HRTM, other analytical methods. And we characterize this material by Raman spectroscopy, XRD, and porosity, surface area, and the pore volume was determined by BET methods. So we could find this material shows high surface area and pore volume. And this material, we use this material for making with other substrate, with some additive to make it to a electrode material, and then utilizing this for demonstrating at least we have shown the demonstration of generation of electricity by igniting tuning the LED in the university logos. So it can be permanently used for 8 hours continuously by using this gum-based electrodes. So how it is happening? Actually, this is things we have, how we have shown this, the synthesized microcarbon out of these gums exhibits high area, and the actual what is the mechanism in this process to make the energy is how we can say the energy, what is the mechanism of the energy production in this method. So they have a lot of micropore and mesopore on this substance, and that is a water absorption and evaporation turn into energy. Evaporation of water that convert into energy. That energy then transferred to the system. So the synthesized this microcarbon exhibits sustainably high surface area along with abundant micro and mesopores, which drives the fast evaporation of water via capillary actions. So this is a very economically easy way to make energy out of this gum waste. Yeah, this whole process we have recently we have published in green chemistry how this recycling of food grade tree gum waste into nanoporous carbon for sustainable energy harvesting. So the next research is just how the tree gum and tree gums incorporate with carbon nanotubes. So we use the gums, and another material is sodium alginate. This is also another polymer plenty available. So to mix with both these material polymers, come and sodium alginate with casting. Actually we made the films by using the casting methods, and so finally this material we used for energy harvesting too. So here you can see how we synthesize two types of hydrophilic and hydrophobic films. So let us see. When you use this CNT gum films, yeah, first one is yeah. Yeah, you can see this is hydrophilic film. This carbon nanotube is related conjugated gum films is completely soluble in water. This is hydrophilic. When you silylated this material, it becomes stable. You can see this material is not soluble in water. So in this way, we can make two types of films. One is water soluble and water insoluble film, hydrophilic and hydrophobic films for various applications. So here you can, in these films, we have produced the energy, continuous energy by using these films. So here, see, this is an LEDs lighting. This connected through the films, so it is giving the continuous energy. So this way we synthesize this tree gum CNT based conducting films. So here in this video, you can see how the energy produced. So when you check it, any part of the film, the current is flowing through the film. So it's why the LED is igniting here. So in this way, we synthesize the 3-gum CNT based conducting films. Yeah, and recently we have started making 3 gums with a silver nanocomposite with other 2D material like MXene conjugate for detection of environmental pollutants. So this is just the composites made out of MXene and the gums, and MXene with the gums and converted into MXene gums combined into making the 3D sponge, then adding silver nanoparticle onto the gum, and we have made a composite of 3D sponge with the silver nanoparticle. This material can be used for SCRS. By SCRS principle, we can use for detection of this sponge for detection of environmental pollutants by using this sponge. So to conclude me, actually, I have shown the 3 gums, bio-based materials, even bio-waste for fabricating of various films, fibers, and sponges for potential energy, environmental, and food packaging applications. And so this work has been supported by the Ministry of Education, Youth and Sports of Czech Republic with European Union, EU support, and with the Czech and American sanctioning, Czech American, this also supported by the Czech American Funding Agency. And I would like to acknowledge Professor Miracelo for supporting this work and our group of PhD students and staff involved in this work. And some of the works we have collaborated with Professor Andreas and Seema Agarwal in the University of Bayreuth. So thank you for your kind attention. If you have any questions, please ask. Thank you so much.
Thank you very much, sir. So if there is any question, then kindly put it in the chat box also. So few questions as well as the comments we have received. Let me just read out. So what is the best technique for cutting electro spun material into small round discs? From the Devasis Zena.
Cutting the electro?
This best technique for cutting electro spun material into small round discs. I think the small this we see.
Maybe this electro spinning is a technique when you make a polymer solution, you can convert into a fibers form. So the starting material is a polymer. Suppose if you have polyvinyl alcohol or any polymer, if you make the polymer in water solution or other organic solvent, then using this electro spinning machine, you can make it fibers. So I didn't understand what is the cutting. Then if you want to make other sponges or everything, you can make a you can do the cutting. Cutting in the means actually short fibers. You can make the short fibers by using some techniques. So
okay, sir. Sir, let me take up another question.
Yeah.
There are lots of appreciations we also receive by the participant. So next question will antimicrobial edible films be toxic to be probiotics if consumed?
Can you repeat the question, sir?
Will antimicrobial edible films be toxic to probiotic if consumed?
Because actually we make the chemically modified. We prepare the chemically modified gums like DDSA based gums for food packaging. So maybe this DDSA we use very small amount. They also have a potential antibacterial property. So these material we use for food packaging, and more toxicity studies is underway. Actually, we are not carried out. We make this product and give it to the biotechnology laboratory to check how the toxicity create, but it is only underway. Actually, we are not completed the work. Actually,
yes. They are asking mainly those like toxic part is if consumed like that. Yes.
Yeah.
Sir, yes. Sir. Any more questions? There are lots of appreciations we are getting in the message from various people. But if any more questions are there, so kindly type it in the chat box. So, sir, you have elaborated lots of this gum use and all those things, and then even those bio-waste applications for the various way, particularly for the energy and all those things also. I don't see any more questions, sir.
Very wonderful talk, Professor Adi. We really enjoyed. So it's a wide range of applications, and coming out with wonderful results and variety of the materials that has been derived and synthesized in your laboratory. It's a good applied type of the work that you have carried out.
Yes, sir. Yes, sir. And the application based.
Yes. Thank you so much.
That also, sir, in the variety race in terms of energy, in terms of foods and the other environmental effects and all the things.
Yes. So I think Professor Lalit, if no more questions, so you can give the vote
of thanks for there is both our
distinguished speakers.
Sir, I will propose vote of thanks.
Yes, please.
Yeah. Okay, sir. Okay.
For both the speakers. Yeah.
So, good evening to all the participants. And today we have a wonderful talks, particularly with the green technology treatment with the bio-based materials by the two renowned speaker, Professor Rasolt Karniak and Dr. Vinod Bhiti Padil. They are having the wide, not only the research are based on the application base and which is covering to the various areas, various sectors. We at the beginning of the presentations of this one on all the facilities also been highlighted very clearly. So with this, the very interesting things which covered mainly are all this is a applications are ranging from all the ranges, even from the nanomaterial, the chemistry people, even from the engineering people who have been in the energy harvestings and all those things like that. So all the topics are covered very nicely. So it is a wonderful talk, we should say, and we should appreciate our two honorable speaker from the Czech Republic. And for giving a valuable time to us, and because of their talks hightings about their research area, so we all by enlightened with the uses, even those who are from the different backgrounds are getting the ideas about how the gums are being used and the various other things. As particularly in the Mizoram, this is basically as the forest parts are widely covered. So here we can see either lots of the from the trees, the gums have been coming out and all those things like that. So so with this hearing the things, how it has been coming up to the applications way, how it has been using, those has been very clearly highlighted by our honorable speaker, the Vinod sir. Sir, with this point, we would like to appreciate from the organizing team from the Mizoram University, and I also like to thanks to our honorable Vice Chancellor for inviting the two such eminent speaker from the Czech Republic, and with this I like to thanks to all the participants and their interest and their appreciations. They all are writing all the appreciative words to us and making us happy or organizing such a wonderful webinar. With this, we would like to conclude today's session. Thank you very much, sir, Vinod sir, and the previous speaker, Professor Rolsop. Also, thank you very much, sir.
Thank you so much for your very nice, kind words. Actually, yeah, it's a great pleasure for me to invite me to give a talk here at Mizoram University on webinar. So in future, we'll have nice collaborations because I know that many of the gums we are still getting from India. So yes, because they consider as a bio-waste gums, because India is a country exporting maximum, is the #1 position exporting gum carya in the whole world. You know, actually, yeah, yes, per our records. So actually, it's so these gums can be used for many potential applications, because they are bio-based, green and sustainable materials for the future development. So you have number of possible for chemical modifications and other treatments for making and like electro spinning fibers and make the food packaging bags or something like that. That India really need this type of technology, because the starting material is plenty in India, as and is very highly cheap materials, economically feasible material available in India. So we could produce these type of bio-based products for much potential applications in India. Actually, yeah. Thank you so much, Professor Tiwari, to actually kindly invite me to present this talk. And especially for I thank to Professor Sambashiva Rao, Vice Chancellor of the Mizoram University, also, and all other attendees. And if you have any participants have any questions, they can write to me, and I will be very happy to interact with them and discuss with them. Thank you so much.
Thank you, sir.
Thank you.
So with this,
yeah, thank you, sir. Thank you, Professor Cernick, also. Thank you.
Thank you. Thank you.
So with this, we will close the session.
Okay, thank you, sir.
Thank you.